Let me welcome you to my presentation on swarm research activities. This is stemming from a cooperation with the Heinrich University, where I, Kalman Graffi, still supervise a PhD student, Ahmed Sharagi, on this topic. I would like to introduce you first to the swarm technologies that are out there and the challenges that are occurring. So first of all, let's summarize what swarms are. We all know them from biology, such as from ants or for fish flocks or birds. They typically interact in the world, 2D, 3D, and technically this is often represented in various grid types so that movement between different points, fixed discrete locations, can take place. Typically, locations can also bear and carry some information, especially if you think about the ants, how they leave some stigmergy, some pheromones on the floor to communicate with their fellow other ants. Then we have objects in the world, which can either be obstacles, carryable things, but they can also have some state, some information. So these are typically passive elements that cannot do anything by themselves, but the agents can interact with. This is typically something like energy source, food, obstacles, enemies, anything that interaction will happen with. And finally, we have this swarm robots or swarm agents, which are typically equipped with some sensors so that they can explore and sense their environment, and local communication ability so that they can communicate with each other in a short distance. They also have typically some grasp and environment modification tools so that they can pick up objects, mark the world, modify the state of the objects. And with this limited set of capabilities, we already have a wide variety of potential use cases and algorithms and challenges to address. So especially the mobility makes quite interesting aspects in the agents so that they can roam around and interact with the objects and with each other and try to resolve some challenges. What kind of application fields are there? This is just a snapshot of example use cases that we have addressed. So for example, we looked at ants searching for food, how to represent that in algorithms. This can be at the same time transferred to EVs searching for energy. Then we looked at average area coverage, for example, through lawn mowers, swarms that aim to cover each grass spot in the area. That means if there's a field somewhere, they can try to visit each location and through that, at the lawnmower example, to cut the grass there. Then we have object coding. This is represented here with the blue spots, where basically the objects are statically placed and the agents aim to get as dense and as close to the objects as possible. This can be, for example, applied to nanobots that address and code cancer cells, but of course the application fields are a wide range. Then we have object formations such as swarms searching for specific elements in the world or placing objects in specific patterns. We also have swarm movement challenges, of course, such as moving like flocks, so to stay close to each other, but not too far, but also not too close. Then we have message passing. So communication plays a great role either through the environment, such as the ants through pheromones, or they communicate directly by passing messages on. And here also potential networks can play a role where basically communication from a sender to destination needs to be implemented through various multi-hop activities. There are various application fields, and I would like to select some of them and show you what effect they have. First of all, we did a survey on swarm algorithms, so looking at 220 papers and basically putting together all of the swarm properties, all of the activities and research challenges and use cases that have been addressed in literature. Of course, they are quite a variety of use cases, but we wanted to give some overview, and I think this is quite valuable. So one of the overview elements that we gave an overview on is on current swarm projects, where basically tiny robots can be bought and large-scale networks, such as for 100, 1,000 nodes, can be set up. So, for example, a very prominent example there is the Kilobot project, which summarizes robots that are roughly as large as a tennis ball, and you can set them up and implement in this prototypical environment swarm algorithms for 100 or 1,000 bots. And then we looked at other application fields, and especially also at simulators, which are very important to evaluate the quality of these swarm algorithms. And here there's a handful of simulators available and still active, and one of them, SwarmSim, at the top row, we also added to the research community, so that we find this is a quite convenient tool to use. Down here you find a citation, so if you want to look deeper into that topic, you are welcome to have a look. Speaking of swarm simulators, SwarmSim is our contribution to that. It's also available on GitHub, and we aimed to address specifically these characteristics that we named as swarm properties to be supported. So especially to have the world that can be marked, to have the objects that can be carried around and can be also marked and have state, and the mobile agents that can interact with the environment and communicate with each other, sense their environment, and implement dedicated swarm algorithms so that we have some emergent behavior. This has been also used in various student master theses and several publications. In its properties, it's written in Python, it's open source, it supports a 2D and 3D world model with either a quadratic or triangular grid. So typically this has some impact on how quickly you can reach specific points in the world. For the algorithms, that typically doesn't make a too big difference. However, here the triangular world is to prefer, because these points are equidistant to each other, and you can have a better representation of shortcuts and a realistic movement. Here's a view from the graphical user interface, where basically these agents are represented. There's this passive objects as well as some markings on the specific locations. Here's the two-dimensional view with the items in the world, and here's some three-dimensional world that I will also go deeper in the next slide. Some words on the simulator. So it's a round-based simulator. So every round, each of the agents is activated and the corresponding solution file is processed, which basically allows the robot or the agent to use its sensors, so to look in for items nearby or for other objects nearby and robots nearby, then to either decide to pick up or drop any item they carry, to walk in a random direction, and to exercise the communication sensing and basically the swarm algorithm that they locally implement. Each agent is considered to be decentrally organized. So basically each agent follows its own rules, how it interacts with the world and what it perceives, and through the various individual activities of the agents, some behavior emerges for the overall swarm. What else is happening is that the simulator is continuously collecting metrics, such as these are that have been defined, such as how many steps the robots take, how many sensing and dropping and picking activities they do, and basically any kind of metric can be implemented. And after a specific number of rounds, the simulation stops, and all metrics are written to comma-separated value files and plots are generated so that they can be scientifically analyzed. What is very nice for the developer of new swarm algorithms is that basically the whole processing of the simulator is quite independent of the specific solution that is implemented for the swarm agents. So basically As I've said, in each round, this solution file is called for each agent, and there the agents can define what they want to do. So for example, here is a simple random walk implemented in which the agents check whether they can pick up something, and then they carry it around and then they drop it. So here for each agent in the world, it checks whether there are items in its surrounding and especially close by. So if there are any items, then the agent takes it, it selects a random direction, it moves there, it selects another random direction for the next step, and then drops it. Here you can see how the simulator looks like in the two-dimensional representation. So basically, the quadratic grid and the triangular grid are shown, and here objects are placed and carried around by the randomly moving robots. Of course, you can zoom in, you can drag and drop the world to get a better look. And you can interact with the world in real time, so you can add in any round that is currently active further objects to the world or delete them. Here you see a three-dimensional representation of the world, again with the quadratic and the triangular grid. And of course it's a little bit more cumbersome to have a look here. So in this algorithm, what has been done is to explore the available space by the agents and marking in bright blue which spots have been visited, and in dark blue which spots have been identified as borders of the reachable world. Coming to the examples that can be implemented, and one of the scientifically nice examples is a swarm coating. And so here the goal is to, for example, represent nanobots coating cancer cells or firefighter robots surrounding and extinguishing fire. So what is given is a set of objects placed in random but connected shape. And it's very easy if it's basically the shape is round and there are no caves and no specific elements in it. But of course, because it's too easy, we look at the more complex cases. And what the agents can do is they can move. They have a one-hop vision range, especially to detect whether they are nearby an object. And they are given the knowledge of the location of one object so that they can walk there. And how do we measure the success criteria for the swarm coating? This is basically when the most distant agent is closer to the object shape than the closest free spot. And for that we introduce some kind of distance. So for example, here is the distance 1 to the object, here is the object 2 to the distance, and if one and we can measure for every here in round blue depicted agent its distance to the object shape, and see whether free spaces are closer to the furthest distance agent, and if this is so, then it's invalid. So the agents have to be as close as possible to the objects. And basically we looked at two kinds of algorithms. One is the leader-based algorithm, where basically one leader scans an entire object shape and then carries the other robots to their places. This is a more centralized approach. And a self-organizing approach, where basically each agent is individually active, and they try to communicate and locally sense the right spots and communicate where movement has to be done and try to solve it self-organizingly. Here on the right you see some valid coatings, where basically the positions of the agents are as close to the object shape as possible, especially taking a look at this hole in the middle. So this spot here, a free spot, has a distance of 2 and there's no closer agent, while when there are closer agents, so when we have more agents, then they need to fill this spot as well. So counterexamples, invalid coatings is when the screen spaces remain free, and then these have the distance 1, while there are agents with distance 2, and therefore this is not ideal. Here the free space has the distance 2, while up here there are nodes with agents with distance 3, so this is also invalid. Here's a free spot with distance 1, while there are agents with distance 2, and so on. So this would be the invalid coding. Let's have a look first at the leader-based coding and how we solved it. So here the goal is that the leader scans first the object shape in total, and then memorizes where to place the agents, also in dependency on how many agents there are. However, this example is limited to shapes of simple caves, such as depicted here, so that they have some inner space. There's a tight gap which allows one node to pass through, but for example not two at the same time. And there are various challenges involved. First of all, to find the entry of the cave and to not block it. Then to fill the trail, the path into the cave efficiently and to not block the trail, and then have a look through comparing how many agents need to be placed, whether for example the spot in the middle needs to be filled or not. Therefore we have some nice algorithm which basically follows as I described now. And the challenges that might occur, as I said, is that, for example, one of the agents blocks the path and the further agents have to stay outside and cannot go in, although these blue areas should have been filled. The same by blocking the entrance, because it is considered as a good spot nearby to the other objects, but it is not, so because then the inner cannot be reached. And then depending on how many agents they are, so let's say there are sufficiently many, so there's, in this case, this black agent should have been placed in the middle with a distance of 2. Now it has a distance of 3. So this is not an ideal, not a valid coating. So in this case, these two blue nodes should move in and give space for the outside agent, while at the other side, if there are not enough agents and we would just blindly fill the gap in the middle as well, then this agent would have the distance 2, while there's a position with distance 1 outside, and that's also not a valid. So, and then by addressing all of these specific challenges, we put together our algorithm, and here it is shown how the solution works. So basically the green agent is the leader agent, which walks around and places the nodes at the right spots. On the left side, there's a way that the middle needs to be left open, because there are just enough agents that it is not required to fill the middle. And as you've seen, the trail has been left open, so this spot in the middle remains open, while on the right it needs to be filled. And because the leader knows how many positions there are and how many agents there are, the leader can make a wise decision on whether to fill the gap in the middle or not. So everything works fine. However, the solution is only limited to this specific kind of cave shape where there's just one tiny entrance. And a more general approach has been addressed in the next solution. In this paper, we looked at general swarm coding of arbitrary but connected objects. So again, here what is given? Given is that each agent has the knowledge of at least one object, so that it can walk there and start the process. What you also have is an arbitrarily shaped connected object shape, and all agents act on their own, so there's no leader now. They need to self-organize to code the object shape. What they can do, they can locally sense their one-hop environment, so basically to know whether they are nearby an object. And then they can also communicate. So let's, especially this is important so that they can tell their neighboring agents, for example, what distance they have. So what kind of challenges do we have? First of all, to find the object shape, that's quite trivial by knowing at least one position, so the agents can walk there. And then to compute their own distance as well as the distances of the nearby agents to the object shape. So for example, here the red agent has the distance 1 to the object. This with the 2 has the distance 2, then 3, 4, 5, and 6. And now with this knowledge, we apply some kind of communication protocol that allows to tell where the free spots are. For example, here the green spot is free. That should be communicated to that distant node, so that all nodes on the path there learn, aha, there's now a free spot. We need to make room so that this outer node can also shift in and find its valid place. So especially we communicate the minimum distances of free spots and the maximum distances of agents. And this we apply in quite challenging shapes, such as with small holes, which could be interpreted as tiny a collection of caves, but also very thin tunnels or different kind of caves. So we looked at really various kind of object shapes which are connected. And the main solution for this approach is that at first, of course, the agents walk directly to the objects they know about. Then they compute their distance of their own and the free spots nearby. And then they broadcast information. So basically, all agents broadcast the information about the agent which is furthest away with the maximum distance. And then they also communicate the free spot locations with the minimum distance. And somewhere in the network, these messages meet. And basically the nodes that are on the path between the most suitable free spot and the furthest away agent, they learn that they are now on the path between those spots. And now, by knowing this, they can all shift by one spot, and basically the node, as it's explained here, so here they identify the distances, and then this node with the distance 1 learns, there's a free spot with distance 1 as well, and here's an agent with distance 2, so I have to move in that direction to make room that this with number 2 can move in my now position. And if the path is longer, then of course this shifting by one step takes as long as the path is long, but eventually the most distant agent finds a valid spot as well. And this is done then for all distant agents until there's no agent that has a larger distance than the closest free spot. Of course, there are some caveats in communication that needs also to be addressed, especially if the messages get outdated or they get into the circular space. So then even when the furthest away node would have found its position, it would still circulate and the information would not get out of the system. It has to be, so all of this broadcasting and state communication need to make sure that the movements are reflected. Then there's real delicate balancing, how to make sure to find the right path where the nodes should move and which nodes should move. Message time to lives play a role. So it's really some more advanced communication protocol that has been involved into this. But what we have shown, so for all of these different cave structures, eventually the coating succeeds to 100% in any kind of seed and start condition we make. And this is quite positive, so eventually any kind of node count leads to successful coating. So we didn't have any kind of failure. Here you see some example with a simple case with just one object in the middle, and here you have a more complex example with a cave, and you see there's first an agent that blocks the road, and as soon as they communicate that they should move, then they start getting deeper into the cave. And especially in the later parts of the video, you will see that at the side there are these continuous movements where basically the whole path that has identified that it's on the critical path between free spot and outlying agent, they all shift by one. So especially here at the top you see it, that they move by one spot, and then here at the bottom, and now they have also reached the perfect and valid coating. So here's for example a free spot with the distance 2, and the maximum distance of each agent is also 2. So this is a valid coating. Let us have a look at the challenges that occur from swarm movement. And there are several examples where swarm activities can be looked at. And the first I want to focus on is photodetective movement, or escape from radiation. So what we have given here is this kind of world where there's radiation or light coming from the left and hits the agents in the middle that have a binary sensor to experience this radiation. So basically they know, oh, there's some light or some radiation occurring to me, but they don't know the direction or the distance. What is the goal of the swarm is to move past the finish line here to the right, where they are out of the active range for that radiation. And what is interesting, I mean, is that this agent casts a shadow, so all agents right to them are not experiencing the radiation. And now they have to make a decision on how to behave, when to move, in which direction to move to reach that goal. And the success of these algorithms is measured in how many rounds it takes to pass the finish line with the whole swarm. And here we looked at two types of robots, of agents. The first group is the battery-powered robots. Basically, they directly move when they sense radiation. So in the first round, they sense radiation, they already move to a random free spot in their surrounding. And the self-charged robots, where basically they wait for one round and then only move in the second round. And to our surprise, the self-charged cohort of agents succeeds in 100% of the cases, and the maximum number of rounds it takes them is 2000. So it's quite quick, the 31 agents to reach that goal. And in 100% of the cases it was successful. While the battery powered, which move directly, they have only a 59% success rate, and they are very close to 5000, which is the maximum number of rounds that we gave the simulation to run. So this is really not advantageous. And here you see some example how this movement looks like. So the red spots, the agents experience radiation and then they move. And what happens is that if they move to the right, then they can stay there. If they move to up, down, left, then they will have to move again. So eventually they will have to move to the right until they reach the valid state and they pass the threshold, the finish line. Another type of movement algorithm that is prominent in swarm algorithms is flocking. So flocks are groups of birds, fish, nanobots that aim to stay together but not too close together. So basically this is the typical picture of fish flocks that you know, or bird flocks that you know, where they keep a specific distance. This is typically called the separation distance. So they are uncomfortable if they are too close. Then there's a safe situation where the distance is fine, so there are no too close agents around, but they are still visible. And there's a critical situation where basically the specific agent or swarm member is getting too far away from the flock, and they want to get closer. So these are the three rings that are existing: separation, alignment, and cohesion rings. And for those, we evaluated the size, the impact of their sizes. We also have the case in a lonely situation where basically no other swarm member is within the vision range. Then basically random movement takes place so that the agent hopefully finds some other swarm members to move to. So we wanted to have a look, what is the impact of these ring sizes? And what we, for example, found out is that at least we need 5 hops for the cohesion ring to keep the network together. So if it's getting too small, then our success rate for keeping the flock together is lowering dramatically. We also had a look at the impact of various separation ring widths, this yellow part on the flock density, and you can also see it. So without separation, the nodes are very close by. With a 2-hop wide separation, they are semi-distance. With a 6-hop wide separation ring, the entropy increases. Here you see an example how this flock algorithm behaves. So you see that basically the separation rings are active and the agents are too close to each other, so they disperse and get further away from each other and distribute themselves around in this world. But at the same time, at the surrounding, they don't get too far away, so that it still remains connected. Let's have us now look at another example, the formation movement. So here we start with a specifically set positioning of the agents, and they need to form some specific formation with their presence. We have analyzed the centralized approach, where basically each of these elements have a specific k-hop range, the visual range. And the centralized approach, there again we have a leader which carries the agents at the right positions. And we have a decentralized approach where basically the agents learn by themselves in which path and which way they have to go. And then they follow it through and use communication to communicate the valid placement, positions, and sensory to see where movement is possible. So what you can basically do is to set up algorithms that restructure the agent positions to reach these formations that can, for example, be a starting point for further algorithms. So especially what we will see is that forming a line is typically a basic building block for some of the algorithms, as building specific formations from a line is easier than from any other arbitrary shapes, because you can count all the agents, and that is more favorable if this knowledge is needed. The next step is basically object formation, where not the agents are to be placed, but there are objects in the world that need to be positioned in a specific pattern. Here at the top, you see how from a beginning of some kind of tubular rectangular shape, the objects are formed into a hexagonal pattern. And here at the bottom, you see how a single agent is placing the objects from a random shape into this triangle. Let's start again. So basically here we have this rectangular space and we have a collaborative placement. So basically the agents identify for which space they are responsible for and which task they have, where they have to put their share of objects. And once they have this knowledge, then they start to do their activities, to place the nodes. And in the lower part, we have a randomly shaped object shape, and basically the one single agent is at first linearizing that randomly shaped object, so that it can really count how many objects it has to carry, and then it places them starting from the top in a very in this specific required shape. In both cases, they have just one hop sensory information and they can communicate. Of course, in the second case, there's no one to communicate to. There, the challenge is more to keep the internal state correctly, to know how many objects there are, where each object needs to be placed, and at what step in the process of placing the objects the current agent is. Having dealt with the movement of the swarm agents, next we come to communication in swarms. And basically there are different communications options. As I've said, we gave the agents the opportunity to communicate with each other when they are in their close proximity, typically one hop, sometimes also several hops far away, representing, for example, Wi-Fi communication, which has a larger range, or Bluetooth communication, which has a lower range. But they can communicate to their nearby other agents. And here the goal is for opportunistic networking is to implement some source to destination routing. Messages are typically required to be passed on in a multi-hop fashion. So every time another agent is met, there's a decision whether the message should be passed and then to decide which message from the buffer to pass on. And also it can happen that there are no nearby agents available, so the communication is intermittent, and then they have to carry the message around. So it's the store carry forward principle, popular in opportunistic networking. And this is a quite popular research field in the closely related to ad hoc networks. And we wanted to evaluate how well the simulator is suitable also to represent that. And therefore we picked the two most popular routing protocols, which is epidemic routing, which basically just floods the network. So every time there's an interaction with an agent, all messages from the buffer are copied. And of course this leads to a very high overhead, but also it is not restricting the distribution of the messages, and therefore this has typically the highest delivery ratio if there are no specific constraints such as through bandwidth or buffer size. And the second approach is the probabilistic routing protocol using the history of encounters and transitivity, which is typically optimizing to reduce the overhead by far, but at the same time to keep the probability high to deliver the messages. So here, every time two agents meet, the routing protocol evaluates how probable it is that the met agent is capable to deliver the message to the destination. Therefore, they all keep a track of the history, whom they met, how frequently they meet other agents and communicated during the meetings. And if there's, for example, a very active and social, let's say, agent met, then there's a high probability to pass on the message. If there's an agent, on the other hand, that has very infrequent, very rare interactions with other agents, then the messages are not delivered, because it's improbable that this agent will contribute to delivering the message to the destination. And then we looked at the impact. Basically, we simulated it again with 200 or 400 agents. Messages are generated every fifth round. And basically what we found out that the maximum message delivery ratio is around 62% in this epidemic routing. Profit is 25%. But of course, this result has to be taken with a grain of salt, because the movement pattern has a high impact, whether they use random walk or we applied random circle walk, and how many agents are in the network, what transmission range they have. So this has a quite high impact on it. But the important message here is that with Swarm Sim we could also implement this kind of communication. Another type of communication that is possible in Swarm Sim is the communication through the environment. As agents cannot just simply communicate with each other, they can also leave markings on the floor. that can be read by other agents. And this is typically the case in for example, ant colonies where they look for food. So in an ant colony, what's happening is that the agents roam out, randomly try to find some food. And once they find food, then they use the same path they took to go there. They take it back and go to their nest. And on their way back, they leave a pheromone trail, which attracts future ants to walk that path to reach the nest, to reach the food source. And this is replicated by the agents. So basically they also move around first at random, and once they find the food, these are data objects with the state of how many food they carry, then they pick a part of that object by reducing the number at the object and increasing it in their local state. And then they walk back through the path they memorized, and they leave a marking of pheromone concentration on the floor. And by that, the next time ants have to decide in which direction they walk. They explore the tiles, the floors, the locations around them, and see what are the pheromone concentrations, and probabilistically based on that decide in which direction to go. So we recreated this food collection algorithm, and we also identified that there are possible ant mills that look like this, where basically the pheromone trails form a circle, and ants walk to death. So basically, maybe they make it to the food source, but then they enter the pheromone trail that leads to a circle, and that might lead to the ants dying in that circle because they run out of food and they get too old. It was quite some challenging approach to set up the corresponding algorithm, but it also shows how well it simulator is supporting to implement such kind of algorithms. So it's really. So we evaluated this setup. We used 10,000 rounds as maximum number, tested, run 10 simulations for each setup. We had 16 food locations with nutrition value of up to 20, which basically every ant picks one piece of it. We simulated 30 ants, so agents, and after 50 rounds, each agent dies except they find food, which resets their hunger limit. So they get a new lifespan of 50 rounds. And we had a pheromone evaporation rate of 4%. So, and what we observed is basically we tested a random walk search algorithm here in blue, which roughly keeps the lifespan of the agent around 40. It's also quite feasible to collect some food. Then we had the regular pheromone-based search algorithm, PSA, here depicted in green, and what we see is that it quickly drops to half of the agent. So basically, the agent don't find any food, and they die at a round count of 50. And here you see also they basically are trapped in the ant mill, and they don't find any more food. But with our ant mill prevention approach, that basically takes influence on where they walk, which kind of when they place pheromones and so on. You see that the food collection increases, and also the lifetime is past the 50 rounds, so they live longer than they should because each of them is finding food. Here's a simulation, how it looks like. So here they spread out, and green is depicting the fresh pheromones, while violet is depicting more the evaporated pheromones. And as you see, there are some trails emerging to the nest, and areas which are not carrying any food, they are not really visited. So this attraction through pheromones, through the markings on the floor, is helping to reach to the destination. Now we can combine these two approaches, so basically communication through the environment and between the agents, and for example at the use case of cooperative lawn moving. So what do we have here given? Here on the right you see various kind of gardens which are surrounded by objects which basically depict obstacles that cannot be passed. And now the task of each of the agents is to cover each spot, each location in this surrounded area. And the correlation is that in lawn moving you also have to visit each spot to cut the grass there. And by cutting the grass, basically you change the state of the location, and this is sensible by the agents. They can experience through the resistance of the cutting motor, for example, whether at that specific position they are at, the grass has been cut or not. And now the goal is to gain from the cooperation of the lawn movers. So if we have two lawn movers at the same time, they should be able to communicate with each other when they're in the surrounding and communicate which positions they have already visited, so that the other agent does not travel there to visit spots that have basically been cut already. And the hope is that, let's say with two agents, the time they need to cut the grass is closer to 50% in comparison to one single agent than to 100%. So there should be a clear time benefit in cutting the grass collaboratively. And so they can communicate through parts. First about the cut grass, so the markings on the location, as well as nearby agents can communicate which positions they have traveled to. So, and this can be also applied in 2D and 3D three dimensions. Of course, then it's more challenging to overlook what is happening, but this is also possible. So, and let's have a look. So basically we had a look at two different kind of approaches. So the breadth first, where basically they add to their current position, they look in their surrounding and add the positions that they have not yet visited to a list. And this list is addressed in a first in, first out order. So first they visit, let's say, this location, then they add the new positions in the surrounding there, but then they first visit all of the previous locations they had experienced. And then the next in the list is basically that has been added are these 3 points, and they explore from a local point of view. And on the other side is the depth first, where basically they have a last in first out approach, where they add all of the positions first to their list, and then they visited the first spot, and then they try to go first in one direction and to explore in that direction stronger. And what they can share is when they meet is basically the visited locations, yet to visit locations, and the borders they know. Here you see an example with 3 agents and one with 6 agents, and we analyzed with several simulations both strategies, and what we find is that all strategies are very close, so it doesn't really give a clear tendency whether breadth first or depth first is more favorable, or whether we mix the groups in the agents that we use. It's all very close, so there's no clear difference, lots of room to improve, especially better pathfinding and better taking into account how lawnmowers actually move, so that they prefer straight lines. But it is a nice playground, and really offers the challenge to identify how to collaboratively move on the lawn best, and how to make a benefit through such kind of swarm-based lawn moving. As we have seen in the beginning, this can be also done in 3 dimensions. So here we have in both cases 2 lawn movers which act in 3 dimensions, and their goal is to reach each spot in this 3-dimensional shape. This can be done in this grid view. This can be also done in this hexagonal view. So it allows us also to explore these algorithms in 3 dimensions. To give a summary on robot swarms, so basically it's a very convenient research field, as the given elements such as the world, what it can do, what it offers, so it can be just marked, and objects that are obstacles and carryable things can also be marked, can have state, and the mobile robots, which are mobile, have sensory and communication abilities, and can interact with the objects who carry them around. That's it. And out of this, you can build various use cases and state various research questions that are sometimes quite challenging to solve. Especially the example with the general coding, that was very challenging to really make it able for any kind of connected object shape to cover it perfectly. It's quite challenging to do. So it's a small set of given elements and a huge variety of potential algorithms to explore. And this can be all done in SwarmSim. So it's really a huge range of use cases. It's matured over various development stages. And in summary, this research field is very promising. So I really see various examples that are interesting to follow. And it also makes lots of fun to address these. So thanks very much for your attention, and feel free to ask questions. Thanks.